So far we have seen that we can take two involutes, or we can take a hypocycloid and an epicycloid and engage them to form gears, which give us a constant velocity ratio and a positive engagement. Now we are going to see that are we stuck with just involutes or hypo and epicycloidal pairs, or do we have the freedom to get more such profiles? For that we must understand why these profiles like involutes or hypo and epicycloids work. So what is the governing law? That law is called the law of gearing, and we are going to derive it here. So let us start with two rigid bodies shown in green and blue here. Both are pivoted, so they can rotate about this point O1 and point O2 respectively. Now the green body is rotating with angular velocity omega 1, and because it is making a contact with this blue body at C, it pushes it and makes it rotate at angular velocity omega 2. If these were nice gears, then the ratio omega 1 to omega 2 would remain constant, and we are going to find the condition which would make it so. For that we will consider this point C as a double point, a point which is situated on the green body and another coincident point situated on the blue body. The point C on the green body will have its velocity directed perpendicular to this line O1C. Similarly, point C on the blue body will have its velocity directed perpendicular to line CO2. Now these two velocities will have a certain relationship. To know that, let us draw a common normal at point C. So this line is normal to the green profile as well as the blue profile at point C. Now point C on the green body and its counterpart on the blue must have identical velocity components along this common normal. Otherwise the two bodies might lose contact, which we don't want, or they will run into each other, which will not happen because these are rigid bodies. So the velocities of these 2 points, if projected on the common normal, would have identical component. Now let us consider 2 more points. By dropping perpendiculars from the center on the common normal, these 2 points we have named as M and N. Now we know that 2 points in the rigid body must have identical velocity components along the line that joins them. Otherwise the 2 points would come closer or fly apart, which cannot happen in the rigid body. So if M is a part of this green body and N is a part of this blue body, then M and C would have identical velocity components along this line, which is the common normal. Similarly, N and C would have identical velocity components along that line. So in effect, points N and M would have identical velocity components along the common normal. But because the way we located them along the perpendicular from the centers, their entire velocity would be along this line. So we can say the velocity of M and velocity of N are both directed along the common normal and are identical. Since both these bodies are in rotation, we can write the velocity of M and N as R into omega. So velocity of M is O1M into omega 1, which should be equal to velocity of N, which is O2N into omega 2. So the ratio of omega 1 to omega 2 must be equal to O2N upon O1M. But these two distances are rather awkward in their geometric description. So let us get something simpler by joining the 2 centers. This line intersects the common normal at point P, and it forms 2 triangles. O1MP and O2NP, both are right angles and have one angle equal, so they are similar. So whatever is the ratio of these 2 distances will be the ratio of their hypotenuses as well, and therefore we get a simpler rule. The ratio of angular velocities is equal to the ratio in which the line joining their centers is divided by the common normal. This statement is called the law of gearing. Finally, since we want the velocity ratio to remain constant, the ratio of these two distances must be fixed, thereby fixing the location of P on the line joining the centers. So law of gearing says the common normal must intersect the line joining the centers in a fixed point. That point is called as the pitch point.